We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India.
Good morning, friends. Myself, Darshan Mehta, working as an assistant professor, Civil Engineering Department, Dr. S. and S.S.GHANDHY, Government Engineering College, Surat. Today I am going to deliver one lecture on laminar and turbulent flow in pipes from Applied Fluid Mechanics subject under the curriculum of 6th semester Civil Engineering students. These are all the contents which are going to covered in my today's lecture. Before starting with the concept of laminar and turbulent flow in pipe, one must remember or aware about what is flow through pipe and what are the various type of losses which are occurred in the pipe. So when the fluid flow through the pipes, then there are 2 type of losses, major and the minor. Now first I would like to give you some brief about the major losses. That major losses are associated with the energy losses per unit length of the pipe, and the minor losses are associated with the bands, fitting, valves, etc. Major losses generally occurred due to the friction in the pipe and ducts, whereas the minor losses occur due to the local disturbances of the flow in the conduit, such as the changes in the cross sections, projecting gaskets, elbows, valves, and some similar items. Okay, so this is the basic differences, or you can say the basic information about the major and the minor losses which are occurred in the pipe. Major losses are the head losses due to the friction factor and the pipe diameter, and it can also vary depending upon the type of the pipe which is used. Minor losses are the small losses which are occurred due to the bands or the valve that disrupt a smooth steady flow. So as we all know that there are 2 type of losses, major and the minor. In the major, the loss which is occurred due to the friction can be solved by 2 equations. One is the D.R.S. and second is the Chase's formula. Whereas in the case of minor losses occurred into the pipe that are due to the sudden enlargement, due to sudden contraction, due to the pipe fittings, at the pipe bends, and at exit of the pipe. So this is the brief idea about the losses in the pipe. Now next we go to the classification of the flow into the pipes. Now in this particular module I am going to the turbulent and the laminar flow into the pipe. But basically in the flow through pipe there are various type of flows like steady, unsteady, uniform, non-uniform, compressible, incompressible, laminar, turbulent, 1D, 2D, 3D flows. So what do we mean by steady and unsteady? Steady flow is that type of flow in which the discharge Q is constant with respect to time, whereas the unsteady flow is that type of flow in which the discharge vary with respect to time. Fine. Next is the uniform and the non-uniform. Uniform flow is that type of flow in which the cross-sectional parameters are constant with respect to time, or you can say in other words the cross-section parameters are constant throughout the whole sections, whereas the non-uniform flow, the cross-sectional parameters are vary with respect to time, or in other words, the cross-sectional parameters may vary throughout the whole sections. Compressible and the incompressible. Okay, incompressible flow are that type of flow in which the density remains constant, whereas the compressible is that type of flow in which the density may vary as per the material. As per the material means the density of the mercury, the density of the oil, the density of the water, like way. Laminar and turbulent. Now basically the topic which I am going to refer is based on the laminar and the turbulent flow in the pipe. So we will go into the depth in the next slides. So I am giving you some brief introduction that what do you mean by laminar and the turbulent. Laminar flow is that type of flow in which the flow having a well defined path and the lines, the flow lines are parallel to each other. Whereas in the case of turbulent flow is that type of flow in which the flow lines are not parallel to each other and the direction is in the zigzag. Then last is the 1D, 2D, 3D flows. 1D flow indicates the one-dimensional flow, 2D flow indicates the two-dimensional flow, 3D flow indicates three-dimensional flow. 1D that is in x direction, 2D that is in x and y direction, and 3D that is x, y and z direction respectively. Fine. So now classification of flow based on the Reynolds number. Previous whatever we have discussed, that is the classification of the flow in the pipe. Okay, now we are going to discuss the classification of the flow based on the Reynolds number. So first is the laminar. Already I told you that laminar is that type of flow in which the flow having a well defined path and the lines, the flow lines are parallel to each other, the streamlines are smooth and highly ordered motion. Whereas the turbulent flow in this, they have no as such well defined path and having the direction zigzag, and due to that there is so many fluctuation in the velocity and very high disorder motion, and most flows encountered in the practice are all known as the turbulent flow. And next is the transition. The flow which are fluctuate between the turbulent and the laminar is known as the transition flow. So this is the basic definition. Now if we correlate with the Reynolds number, so if your Reynolds number is less than 2000, then we can categorize as a laminar flow. If the Reynolds number is greater than 4000, then we can categorize as a turbulent flow. And if the Reynolds number is in between 2000 to 4000, then it is known as the transition flow. So this is the classification of flow which is based on particularly the Reynolds number. Next, see this example. In the first diagram you just see the laminar and the turbulent flow regime of candle smoke. When I start the candle smoke, initially we can say that it is a laminar flow because it having some well defined path. But once after some time you just see the smoke is spreading outside. Okay, so when there is a change in the direction, when there is a change in the path of a smoke, we can say that the flow is going to convert from laminar to the turbulent. So in this particular example, I am explaining you both the types of flow. Initially, when you start the candle, initially there is a laminar flow, but after some time interval, the laminar flow is converted into the turbulent. You just see into the diagram. If we go to the next diagram, figure number A shows you the example of laminar flow. Okay, I already told you in the definition that laminar flow is that type of flow in which the flow path flow having a well defined path and they are in a straight plane, means their direction is a straight. So you just see in the diagram the red line, okay, the arrow shows that it is the velocity direction, and in the diagram the die trace that is which is indicated by the red color, that is the injection, dye injection. You just see it is flowing into the well defined path and having in the straight direction. But in the figure number 2, which shows the turbulent flow, you just see the die trace having a zigzag manner, okay, zigzag manner. So the behavior of the colored fluid injected into the flow in laminar and the turbulent flows in a pipe. So this is one of the example, or you can say this is the some of the images which we can say that how the laminar and the turbulent flow can be defined. Now another example, water exiting a tube. In the figure number A, you just see the water flowing rate is very low. Fine. And in the second figure, you just see the water flowing rate is very high. So if we take the example of laminar and turbulent, then figure A can be called as a laminar flow because at a very low rate. And in the case of B, we can say the turbulent flow at a very high flow rate. Means my trap is open, my discharge is very high, and if the discharge is very high, my velocity is always high. Q is equals to A into V. Fine. Now Reynolds experiment. As we have categorized the flow into based on the Reynolds number, so we must aware that who is Reynolds and what the Reynolds experiment says. So Reynolds experiment in 1883, Osborne Reynolds, with the help of some simple experiment, demonstrated the existence of the following two type of flow. Now which two type of flow, as already we have discussed that we are talking about the laminar and the turbulent flow in the pipes. So the same two type of flows is discussed by the Reynolds in 1883. Means he has one simple experiment in which he has demonstrated, he has applied his principle, and then he come to the conclusion and categorize these two flow, that is laminar and the turbulent. Now in this particular diagram, the water was made to flow from the tank through the glass tube into the atmosphere. You just see into the diagram, on the top there is a tank containing a dye. Okay, so water was made to flow from that particular tank which containing a dye, and when I open the valve, the water which made to flow from the tank through the glass tube into the atmosphere, so it will go into the downward side. Now when it reaches to the particular point, means where it is written that is the water, at that particular point the velocity of the flow was varied by adjusting valve. Now if I open the valve, whole valve, the velocity will be high, and if I close the valve, or I can say if the valve is slightly open, then my velocity will get fluctuating. Means my velocity either it may less or either it may high. But if I can do some open close of the valve, then there will be some situation arises for the velocity fluctuation. Okay, then the liquid dye was introduced into the flow at the bell mount through a small tube which is shown in the figure. You just see at the tank, the tank, near the tank there is a constant head tank. Constant head tank means this is my allowable capacity to store the water, means to store the water into the tank. Then this is the glass tube from where the water is passing through the water is passing and it will get delivered to the atmosphere. And then next is the dye filament. With the help of dye filament, the water is smoothly supplied into the pipe. And last, the regulating valve. What is the use of regulating valve? The regulating valve is used to regulate the flow of water, either high, either low. Means we have control to adjust the pressure, we have control to adjust the valve. Okay, so that what will happen, the velocity will also in the control as per our means as per our work, if we want to increase the if we want to increase the discharge means Q, then automatically the velocity of the flow is also increases. So this is about the general procedure of the Reynolds experiment. Means Reynolds have one simple experiment in his lab, and he has just modified and applied some principle, and based on that principle he came into some conclusion and categorized the two flow into the laminar and the turbulent. And how he has categorized that we will see into the next slide. He has developed one equation, that is Re is equals to rho Vd upon mu. That is the formula of Reynolds number. Fine. So this is about the procedure as already I discussed you. Next is the next is the example. Now you just see the diagram. Very well defined path. Water is flowing. The diagram shows the water is flowing into the glass tube which having a well defined path. If I can go to the next example, that is a transition. You just see transition is the combination. Sometimes it is very smooth and it having zigzag, again straight, again zigzag, like that. Transition is the fluctuation of the laminar and the turbulent. Means for a certain time interval the flow, the water flow is in the straight direction. After that, after some time interval the water flow is having a zigzag direction. And the last is we have the turbulent. So you just see the turbulent having the zigzag. You just see, just observe the diagram. There is some zigzag in this particular diagram. So this way the type of flow based on the Reynolds number can be categorized, or you can say can be classified. Now as I told you that the Reynolds equation is Re is equals to rho Vd upon mu. Okay, so Reynolds from his experiment found that the nature of the flow in a closed conduit is depend upon, means which are the factors from where the nature of the flow is depend. So first is the diameter of the pipe, that is capital D, then the density of the liquid rho, viscosity of the liquid, that is mu, and the velocity of the flow V. Now by combining all the above factors, all the above variables, Reynolds determined a non-dimensional quantity which equals to rho Vd upon mu, which is known as Reynolds number Re. It is dimensionless, it is unitless. Okay, so Re is equals to rho Vd upon mu. He has developed this equation after doing certain experiment in 1883. Okay, so on which tank he carried out the experiment? The simple tank which is in his lab, he modified it and carried out some of the experiment and categorized the flow and developed the formula, that is Re is equals to rho Vd upon mu. In general case, the D is replaced by L, which is known as characteristics length, and thus we have the equation Re is equals to rho Vl upon mu. Okay, so just by replacing the D by L only. Okay, so Re is greater than 4000, the flow is turbulent. If Re is between 2000 and 4000, the flow is unpredictable, which is also known as transition flow. And Re is less than 2000, the flow is known as the laminar, or you can say the viscous flow. Now characteristics of the laminar flow. There is no slip at the boundary and the flow is rotational. Now no slip means as we have the well defined path of a laminar flow, or you can say of any kind of flow, that's why there is no slip. Slip means if there is a zigzag, then there will be the fluctuation. Sometimes it may high, sometimes it may very low. Okay, and the flow is rotational means my flow is going to be flow only in its own axis, not outside the axis. That's why it is known as the rotational. Rotational is also one type of flow. Rotational flow and irrotational flow. Rotational flow is the flow which can be rotate in its own axis. Okay, and irrotational means the flow which can rotate outside the axis, means inside its own axis as well as the outsides. Due to the viscosity, as already I told you that if the Reynolds number is less than 2000, the flow is also known as the viscous flow. So whenever So due to this viscosity, there is a shear between the fluid layers, which is given by tau is equals to mu into du upon dy. Shear stress, we can also say that shear stress is developed between the fluid layer. Why? Because due to the viscosity, okay, which flowing into only in the x direction, okay, and due to this viscous shear stress, there is a continuous dissipation of the energy, and for maintaining the flow, energy must be supplied externally. Means there is some dissipation of energy. Dissipation of energy means there is some conversion of energy from potential to kinetic or kinetic to potential. Fine. And for maintaining such type of conversion, the flow energy must be supplied externally. Externally means other than these two energies, means other than this kinetic and the potential. Loss of energy is directly proportional to the first power of velocity and first power of viscosity, and there is no mixing between different fluid layers. Okay, as if you are aware, there is one topic in the boundary layer chapter, mixing length theory, which is given by Prandtl. Okay, now I think you all are aware that Prandtl is nothing but he is the father of this fluid mechanics, von Prandtl. Okay, Ludwig Prandtl. Yes, Ludwig Prandtl is the father of the fluid mechanics. Okay, so no mixing between the different fluid layers means, so if in the case of turbulent there is a mixing between the different layer. Why? Because the direction of the flow is in the zigzag, means one will strike to another, other will strike to third, third will strike to fourth, like that. But in the case of the laminar flow, they have a well defined path, so that the flow of the water is very smoothly. Now these are the example of the laminar flow. Flow pass through tiny bodies, underground flow, movement of the blood in the example, flow of oil in measuring instrument, rise of water in the plants through their roots, then flow of oil in a measuring instrument, then rise of water in the plant through their roots. Okay, you just see the diagram. The diagram is of the laminar flow. Okay, if you want to see these content, then I already mentioned the source, that this image and this particular material is taken from the D.S. Kumar reference book. Now we go for a turbulent flow. Turbulent flow is that type of flow in which the path of the flow is having a zigzag direction. Okay, turbulent flow is characterized by disorderly and rapid fluctuation of swirling region of fluid, which is called as eddies throughout the flow. Means if there is a zigzag direction, eddies will be generated. This fluctuation provide an additional mechanism for momentum and the energy transfer, and as a result of that, turbulent flow is associated with a much higher value of friction, heat transfer and mass transfer coefficient. Now in the starting of my lecture, I told you that there are two type of losses which is occurred into the pipe. One is the major and other is the minor. So major loss are occurred due to the head loss due to the friction. So same turbulent flow when associated with much higher value of friction. How? Because there is a fluctuation in the velocity, there is a fluctuation in the flow. Fine. Now next, see the diagram, figure number A and figure number B. First figure is before the turbulence, second diagram is after the turbulence. The intense mixing in the turbulent flow brings the fluid particle at a different momentum into a close contact and thus enhance the momentum transfer. In the first case, there is no turbulence between any fluid particles, but if I change the momentum, if I change the time interval between all those fluid particles, all fluid particles are mixed together, and you just see in the figure number B, that is after turbulence, okay, which enhance the momentum transfer. It means that first momentum is transferred to the second, second to third, third to fourth, but to whom those fluid particles are into close contacts. You just see the diagram. From the diagram it is easily understood by you that when there is no any turbulent effect in on a fluid particle, they are safe and they are in a proper manner. But once the turbulent came into action at a different momentums, it will enhance a momentum transfer. And you just see in the diagram, all are mixed together, all are in a close contact, but they are mixed together. But in the case of before turbulence, all are in close contact with of a same parameters. Now this turbulent motion is classified into various types. Number 1, wall turbulence, free turbulence and convective turbulence. Wall turbulence is nothing but it occurs in the immediate vicinity of solid surface and in the boundary layer flows where the fluid has a negligible mean acceleration. Means where it occurs. Okay, so in the previous diagram you just see at the initial stage it occurs, means wall turbulence occur in very immediately, means in on a immediate vicinity of a solid surface in the boundary layer flow where the fluid has a negligible mean acceleration. Means wall turbulence takes place in very immediate form. If we talk about the free turbulence occurred in a jet, wakes and mixing layer. It is a free, means there is no turbulence into it. So the best examples are jet, then you can say the wake, mixing layer, like that. Convective turbulence, it takes place when there is a conversion of potential energy into kinetic energy by the process of mixing. As already I told you in the previous slide that there is a conversion of energy, okay, that is potential into kinetic or kinetic into potential. So convective turbulence takes place when there is a conversion of potential energy into the kinetic energy, means at the time of mixing. Okay, at the time of mixing there is some conversion into the energy. Now what are the characteristics? So the velocity distribution in the turbulent flow is more uniform than in the laminar flow. Fine, more uniform than in the laminar flow. In the laminar flow, the velocity gradient near the boundary shall be quite large, resulting in the more shear. And in the turbulent flow, the flatness of velocity distribution curve in the core region away from the wall is because of the mixing of fluid layer and exchange of momentum between them. As already I told you in this particular diagram, that after turbulence and before turbulence, you just see when the turbulent came into action, okay, all are mixed together and everyone have its own momentum, means different momentum, all fluid particles having different momentum, but they are in close contact. And how? And it enhances momentum transfer. It means x parameter momentum is transferred to y parameter. Barabar, when the turbulent came into action, at that time x fluid particle moment transferred to y fluid particle. Fine. So that is about the characteristics of the turbulent flow. Now what are the examples? So blood flow into arteries, oil transport in the pipelines, lava flow, atmosphere and the ocean currents, the flow through pump and turbines, around airlift wing tips. I am also going to share you one lecture on the turbines also, which is already in your syllabus, that is module number 4, that is turbo machinery. Soon I will going to share this on this particular platform. Now what are the comparisons between the laminar and the turbulent flow? The velocity distribution which is paraboloid in laminar tend to follow the power law and logarithmic law in the turbulent. Means the velocity distribution which is paraboloid in the laminar flow, okay, But in the case of the turbulent, already I told you in the previous slide, in the turbulent flow it is more uniform. Uniform means continuous. But in the case of laminar, it is a paraboloid, which tends to follow the power law. But in the case of laminar, as already told you, the velocity distribution is uniform. So they have to follow the logarithmic law in the turbulent flow. Random orientation of fluid particles in the turbulent flow give rise to additional stresses, which is known as Reynolds stresses. Where in the case of laminar, which type of stress is? Shear stress. Tau is equals to mu du by dy. Found. Then due to the zigzag direction of the flow, eddies are formed. Okay, but in the case of laminar, no eddies are formed in the this laminar kind of flow. Okay, because in the laminar flow, the direction of the flow is having very well defined path. Okay. So this thing, is about some brief about the turbulent and the laminar flow. These are all the references which I have used for preparing this lecture. Means some of the content I have taken from the R.K. Bansal, some of the content I have used from Rajput, and some diagram already I showed you into the slide that I have taken from the D.S. Kumar. So thank you for listening me. Goodbye. Stay safe.